is something that I expect you to know from before calculus. So on one-to-one onto functions and bijections, as if both of the properties are satisfied, that's what's called bijection. But one-to-one onto examples come primarily from calculus. We will take it to the next level in the abstract setting of sets. Okay, but for the time being, we'll just set it aside. And but I might assign a little bit of in the next homework some to refresh your memory about this. Okay, so you have seen one-to-one on functions, right, in the past at some point. The other one, so this is what we talked about last time. The equivalence relations. That just the last topic was what you see here is an extra metaphor for equivalence relations. That's gluing, and specifically in topology. And so we probably will revisit this later because it's such a good topic. Gluing, take a piece of paper, glue edges together one by one, and then you create this is a cylinder, right? So point by point, so you indicate this corner, it'll assign with that one, and so on, okay? But you can also make a twist, right? If you make a twist first and then you glue it together. Okay, so looks familiar? Does it look familiar? No? This just doesn't look familiar?
I mean, it's a ring.
No, it's not.
It's twisted, never mind.
Okay, so it doesn't look familiar?
Didn't we talk about that last time?
No, I thought maybe.
Yeah, maybe, I don't know.
Twist?
Yeah.
Nobody's seen this before?
Like a roller coaster?
What?
Like a roller coaster?
I don't know. I don't think so. They do make a twist, but then when you come home back, right? Well, actually, I don't.
Like, like the circle.
I mean, I haven't. It's been a while for me. So you go on a roller coaster, then you make all the twists, but then you come back. You don't come back where you start the same way. You leave this way and then come back this way. I don't think that happens. I think you make a full turn and come back the same way as you. In the same, the train faces the same direction as it was when you just boarded it, right? Right. So, well, that's not it. It's like a roller coaster. Then after all the twisting, you come back facing the opposite way.
So is there a common name for that?
Yes, there is. I cannot believe nobody knows the name for it. Anyone? Looks familiar?
I know what it is. It's the one-sided.
Right. So, well, that's right. One-sided surface, known as. It's certainly not a calculus course, but yeah, if you were interested in mathematics, this is probably best thing to get started with really exciting things. The Mobius Band.
To what?
The Mobius Band. Well, Mobius was just a mathematician, that's all. But it is a one-sided surface, so you can. This side is the same as that side. Okay, so you cannot get from this side to that side without you crossing. Okay, so that takes you all the way to things that have no orientation, such as it's possibly our universe is not oriented, which means that if you take a trip and then you come back and you will be your own mirror image. So your heart will be on the wrong side, maybe. Well, they say it might be impossible because some of the molecules, if they would take that trip, they would simply fall apart. They cannot exist in a mirror image of theirs would not be possible. So maybe does it prove that the universe is orientable and has only two sides, sort of? Then it's unclear yet, but it is certainly many interesting things and you can do it with nothing but equivalence relations. Okay. So we'll revisit this. I just will have one more picture. Mobius Band. Okay, everybody should know it. Every math major. And there have another picture just for you to Oh, here it is. choose another app. Paint. Always. Okay. Okay, so that's the same idea, only three-dimensional. Oh no, that's not the same idea because there's no twist. This is without a twist. So let's not twist ourselves too much. But that's how far you can go with equivalence relations. So you see what has happened here. What?
Reflection.
No, look at it.
Well,
It's still back of his head. It's not a reflection. I mean, if it was reflection, you would see his face, right? If it was a mirror up there, we would be looking at his face, right? We're looking at his back of his head again. So what has happened here? It's the same room, and it's the same person, naturally. He sees himself in front of him because the front and back of the room have been identified with an equivalence relation, sort of. So, almost like a circle. Okay, well, it twists your mind, I know, but so we'll revisit this later. But at this time, we're moving to something more mundane, but absolutely unavoidable. This is another mundane but absolutely unavoidable topic, but we'll move to something else, and that is mathematical induction. Okay, so mathematical induction. So does it sound familiar?
Yes.
Okay, so do you remember anything?
The n is implied in n+1.
Okay, but do you have any particular proof in mind? Maybe. Did you may have, I'm not sure you did anything in calculus, did you?
No, I did this in discrete structures.
Okay, yeah, that's a good place because discrete, you move on slowly through step to step rather than continuous, and that's where induction is so helpful. So I'll pick one proof that let me start with something that is you see. So in calculus, and the proof also has something proof independent of induction. So this one plus 2 plus 3 plus n. Which is what? If you remember, do you remember the answer to this one from calculus 3, or maybe, well, some of you are still taking it. So, okay, well, the answer is n plus 1 over 2. By the way, the sum of these numbers, so the sum of the first n consecutive integers supposed to produce an integer. Why do we have a fraction?
They're all rational numbers. Well, an integer is part of a rational number. A rational number can be expressed.
Well, so yeah, but still, it looks like a fraction. Why is it an integer?
Because on the top you have the plus 1, which makes the n either odd, and if it's odd, then it'd be two odds multiplied by two.
Right. Right, that's the logic, right? So just in case, unrelated to mathematical induction, but it is a good way to use what we have been talking about, and either n is odd, then n plus 1 is even, or it's even, then it's even. So that one of the either n or n plus 1 is even, and that's why it's divisible by 2. The numerator is divisible by 2, so it is in fact an integer. Okay. Now the proof is this is a the arithmetic progression, right? So add 1, and this is the sum of the arithmetic progression. So it's what you see. It's like as opposed to geometric progression when you do multiplication. So geometric progression, when you have your bank account, you get 10%, 5% yearly. That's geometric. If you contribute every month $100, that's arithmetic progression. So that's what it is. So you go from 1 to 1 plus 1, then which is 2, and then 2 plus 1, which is 3, then 3 plus 1, which is 4. So that is arithmetic progression. And then you add the sum. Then you want to evaluate the sum based on that. So if you want to know how much you have, and that all fits into calculus 3 series. That's like a series. Okay. So, but we are not going to infinity. That's the difference. And in fact, if you keep adding 1 plus 2 plus 3 and so on, you will end up at infinity. But instead, we just want to come up. We want to prove this formula. So this is what we want to prove. Okay, and the idea is, well, let's start with the idea that is not, does not require induction. And the idea is fairly simple. It is like this. So you take, you draw squares. You draw squares. Let me try. You draw squares, as many as necessary. Well, just to get the idea. Okay, so what we are facing here, 1. So I'll take 1 from here. This is 1, 2, 3, 4. Looking for a pattern. 5 and 6 and 7. Okay. 0, 1, 2, 3, 4, 5, 6, 7. Okay, so they are arranged in such a way that it suggests a pattern in this summation. Well, how would you? Well, up to 7, it's pretty much a lot of computations to compute 1 through 1 plus 2 plus all the way through 7. But looking at the picture, can you tell me what it is based on the picture?
Previous term plus 1.
What?
It's the previous term plus 1.
Yeah, right. That's how you get the next one. What is the sum? Look at the squares that are present versus the ones that are not. This is the sum. The sum we're trying to evaluate is here. Okay? Let me try to suggest to you.
You did like 1/2 based on type?
Oh, close. So we certainly know how many squares there are in the square, right? How many?
8.
What?
8 by
8 by 8 squares, right? To begin with. So now we just need to throw out the rest. And you can see I marked one with green and the other one with blue. What's the relation?
Those are identical.
These two are identical. Okay. And what's left? So 2 of these, one of which we're looking for, and then what's left? These diagonal,
Which is 8.
which is 8. 8. Okay, so 2 times x, which is unknown, plus 8 is equal to 8 times 8. Okay? So once again, 8 by 8 squares, 8 on the diagonal. So 8 by 8 squares, the total is split into 3 parts. The green part, the blue part, and the diagonal. Okay? And so that's what I have. 2x, those two big triangles, plus 8 diagonal. Okay? So, well, then x is equal to 8 times 8 minus 8 over 2. Okay? It doesn't really matter what the actual number is. It doesn't make any difference whatsoever. We want to use this idea to come up with the idea for n. So was this? So we replace now every n with every 8 with n, right? So it's really makes no difference what we have here. So start with 0. So this will be n minus 1. No, not well. Okay, I wasn't quite right. So we are doing summation from 0 to n minus 1. Okay, and now we want to figure out what the total sum is. Well, I guess I want. No, I want n. I want n here. So n is equal to 7 actually. Okay, 0, 7. From 0 to 7. Okay, so okay, so what's the answer then? 1 plus 2 plus n, or I put a 0 here just in case. Same thing, is equal to what? So forget about 7, we're talking about n. Well, what's the total? It is a full square. How large is it? Almost. It's n plus 1. Yeah, we start at 0, so n plus 1 squared. The total square is n plus 1 squared. Okay, and now we subtract. Well, I don't really want to subtract. Actually, that might be a bit confusing. So let me just put it this way. So the square is n squared minus 1, and now we are the diagonal. How large is the diagonal? Diagonal n plus 1 again, and then twice our sum. That is now our x we are looking for. Okay, so this is what we've got. 2x. So the whole square, n plus 1 plus n plus 1, so n plus 1 squared, the number of squares. Okay, the diagonal has exactly n plus 1 entries, and then the two triangles, it's split into the square into two triangles. Each of them supposes x is what we're looking for. So we solve it, and then we have the answer. So x is equal to, what is it, n plus 1 squared minus n plus 1 over 2. Okay, so that certainly is one formula. Well, that doesn't really. So that's the answer. There is a way to simplify it. Let's simplify it because we're gonna continue on. This is a good formula because it's easy to remember, but probably we can do better than that. N squared plus 2n plus 1 minus n plus 1 over 2. So we're getting what? N squared plus n plus 2 over 2. What? N squared plus n. Right. I'm sorry. Yeah. Okay. So minus over here. Doesn't want to work. Let's run this thing to date. Minus. N plus 1 minus. So 2n plus 1 and as planned and n plus 1 over 2. Even though this probably is the best for our purposes. What is wrong with this? What? Okay. Okay, what is the purpose? The purpose is to reprove this formula with induction. Okay, so induction is the idea of expanding statements from the most elementary to infinity, to infinitely many statements. That's probably the very first thing to observe about this. That most of the theorems are not about any particular number or any particular situation, but rather usually about infinitely many situations. So this formula in particular, this formula specifically is about each n. So it's true for each n. So, but you can when you're trying to understand the formula, or just to discover especially what the formula should be, or if there is any formula, you start with lower values of n. Okay, so not like this. We jump to conclusion, which is okay because the proof may have been similar to something in calculus, but usually you start with a lower dimensional, lower level statement. So such as well, the formula, suppose the formula is already known. So this is the statement that we have designed. So sum k from 1 to n is equal to n plus 1. Well, let me take the other one. N squared plus n over 2. Okay, so to be proven in the full generality, because it's true for every n, okay, but what we're doing here is we can look at, for example, P1. So once again, what I'm talking here are these are propositions. So statements that may or may not be true early on, okay? So P1 is, all I have to do is just replace n with 1, so summation k from 1 to 1, from 1 to 1, k, and then what is it equal to? It's just simply 1. Right? So, and then that's the left-hand side, and the right-hand side it will be 1 plus 1 over 2. So that checks out. Okay, so testing a formula. A formula is might be complicated, but really it's up to you to test it. So, and then if you feel that the case is too simple, try more. That's the second one. Okay, so it's 1 plus 2. Which is 3, okay, and then you go with your formula now this time. So n was equal to 1 here. Now n is equal to 2. So then you have 2 times 3 over 2. It is equal to 3. So once again it checks out. Okay, so we can see that at least in the beginning of the sequence of propositions, the first ones are correct. Okay, so the idea of induction is not continue doing this, but rather now demonstrate that Pn implies Pn plus 1. Okay, that's the induction. So think about it. So demonstrate this one statement. That's one statement that you need to prove. That read it carefully. We've seen this a few times by now. So what we're saying here, if, so we're not saying that Pn is true. We're saying that if Pn is true, then Pn plus 1 is true too. Okay, so that's what we need to demonstrate. If we prove it, so if that does happen, then how do we continue? Then it will be P1 implies P2 implies P3 and so on, and then which means that we have all of them, right? Okay, so let's do it. So it is crucial that there's a starting point, obviously, for our proofs. Okay, so we have 2, in fact. So let's just try to prove it. Usually it's not a big deal, or at least by design, it's not going to be too much of a hassle. So show that what I'm doing is I'm rewriting that statement at the bottom. Pn implies Pn plus 1. And the statement Pn is still here. This is my Pn. What we're trying to prove. Okay? So I'm rewriting sum k from 1 to n is equal to nn plus 1 over 2. So that's Pn. And here I'm carefully writing out Pn plus 1. Replacing each n with n plus 1, that's all. So summation k from 1 to n plus 1 k is equal to n plus 1, n plus 2 over 2. Okay, was it too quick? So once again, replace n with n plus 1. So it's substitution. That's all this is. Okay, so there are many ways to proceed here, and you don't know which one is better. So in this particular case, well, if you have any suggestions how we get from one to the other. What?
You simplify.
Simplify which one?
And start with the right. Just or
Okay. So the idea might be to take the one that we want to prove it and move stuff around so that the expression on the left would appear there. So in other words, this is the plan. Transform this into something familiar. Well, hopefully that summation up to k would appear, and it is really not too hard because after all it is summation, so we know what this stands for. So where is the summation up to n? We have just one extra term. So what should I write here? So this summation from 1 to n plus 1, I want to look where in this expression is a summation up to n. Well, let's put it this way: 1 plus 2 plus k plus plus n plus n plus n plus 1. Okay, so is that the same thing? And now what I have there in pink, this is it. No, this is it. Summation up to n. Remember sigma notation, right? So summation up to n, and then we just have an extra term. So this is equal to sum k came from 1 to n plus 1. And then now this is the magic words that we always use by inductive. There is a good expression here.
by induction is what I'm voicing.
By inductive assumption. I want to emphasize that this is an assumption. Okay, so we are assuming something that has not been proven yet. Okay. So once again, we're proving Pn implies Pn plus 1 without actually knowing ahead of time that Pn is true. So we only getting from A to B, that's all. Can you get to point A is just beyond the point at this time. Okay, so we assume that Pn is true. That's the word assumption comes from. And then by inductive assumption, we know where is the inductive assumption. This is the inductive assumption. Right here. Pn is the inductive assumption. Okay, so that summation up to k is, according to inductive assumption, is n plus 1 over 2. Okay, n plus 1 over 2. Okay, and then we still have n plus 1. Okay. So is it clear what has happened?
Why isn't the second term not divided by 2 as well?
No, n plus 1 came from over there. You see the green circle? That is the summation up to n, and then there wasn't one extra term with no division. So this you were asking about this point over here. Summation up to n plus 1 is summation up to n plus the last term. This is the last term.
It's not the same as what you got up on the top right, is it?
Well, we'll see. So that's the next question. Is it the same? This is the same. So n plus 1. So what we're proving is the transition from the summation side, which has, by the way, why do we dissatisfied with that? Why do we even want a formula? Because of this. Dot dot dot. When you have dot dot dot, you were pretty much admitting that you don't know what's going on there. Every time you're doing things such as say limits, if you have a dot 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 there, either it is a Riemann sum or any kind of limit, you cannot evaluate limit directly. So all the methods of limits won't be applicable because no matter what the pattern of the terms is, you know where the terms go, but when you sum them up, you're getting more and more terms, so you don't really know where things are going. You can end up with infinity or not infinity, you don't know. But when you have an explicit formula, which is exactly what we're pursuing here, then you just take the limit n plus 1 over 2, where does it go when n goes to infinity? It's clear, right? Where does it go? To infinity. Okay, so, but ahead of time, well, not this formula is really simple, so you could have guessed that the whole thing goes to infinity, but because it jumped high and high and higher, but in general, having an explicit formula is advantageous. And by the way, the proof will be fully applicable to every arithmetic progression. So, yeah. So that's the good news. Okay, so we're looking for a compact formula rather than infinite formula with dot dot dot. We have a compact formula which allows us to do algebra with what we're looking at. So with that the only thing remains is to demonstrate that this is the same thing, and it is not hard. So I could, as it was actually originally suggested, I just expand here. I have n squared plus n plus 2n. I'm sorry, this n squared plus n plus 2. Okay, over 2. Okay, and then we expanded this. Let's expand that. I have n squared plus n plus 2n plus 2 over 2. So it is the same. Okay, so as has frequently happened, this is more like analysis rather than actual proof. So because it takes some time to sort things out and frequently discover the right way of doing things. So now once everything is in order at hand, we can certainly write the proof in a more careful way. So that is certainly is. Let's do that. Okay, so all the parts are here. Just all we need is a bit of writing. We're finished with thinking, and we're progressing to writing without almost any thinking left. So theorem: sum k from 1 to n is equal to n plus 1 over 2 for any integer n larger than or equal to 1. Okay, proof. So this is called base of induction. The sequence of statements that has to start somewhere, so we start with the base say n is equal to 1. So there are two steps, and this is the simplest one. So let n equal to 1. We already did the work, so we can just write out then sum k from 1 to n, k is equal to summation k from 1 to 1 k, which is 1, which is equal to 1 plus 1 over 2. True. So the base of induction is proven. Okay, now step of induction, which is what we just did. This whole page devoted. This part is devoted to step of induction. So this is the step of induction, progressing from Pn to Pn plus 1. So suppose or assume, so inductive assumption. Well, let me use that word again. Inductive assumption is, well, is what we're trying to prove. So in other words, summation k from 1 to n is equal to n plus 1 over 2. Okay, now you probably a good idea just at this point say what you're going to do. Let's demonstrate, or let's prove that that summation k from 1 to n plus 1, k is equal to n plus 1, n plus 2 over 2. That's the inductive step. Okay, so we already know that all the computations are right here, right? So this is probably, I just rewrite this in order to demonstrate that this indeed works out. Okay, so so the idea is to substitute. So compute sum k from 1 to n, k, which is n plus 1 over here, sum k from 1 to n plus n plus 1, equal to, now use the inductive assumption, our inductive assumption, and substitute. So this will be n plus 1 over 2 plus n plus 1. Okay, and then simplify. So it will be n squared plus n plus 2n plus 2 over 2, and we just we can factor it out if we like, but it's certainly n plus 1 and plus 2 over 2. Okay? So end of proof. Any questions? Yeah? What? Okay, so the variety of problems you can address in this fashion is just goes throughout mathematics. That's why it is unavoidable. All kinds of formulas. You can do it with say any kind of sums, for example, anything in a theory of series would be applicable, because every time, what is the difference? Well, what happens to the series every time you add an extra term? Okay, so you know something about this, and then you add an extra term, and then you ask yourself what happens. Does this formula is preserved? And then more frequently you might be able to discover that it does indeed continue on. Okay, so that's the idea. One thing before we move on, I want to more examples. I want to point out the importance of the base. The base of induction. So sometimes it's so obvious that it is you might be tempted to skip over that part. As you can see, indeed, this is the hard part. The inductive step is the hard part. But if you do not do the base of induction, then you're skipping over something very important logically. So your sequence of conclusions, right? Where is it? Here. The sequence of conclusions have to start somewhere. Okay, so P1 or wherever you choose to start is you can conclude something about Pn only if you have a starting point. Otherwise, just because you have demonstrated Pn implies Pn plus 1 is not enough. In fact, I could give you an example. Pn is this statement, n larger than n plus 1. And forget that it's not true. But if you assume that you do, and that's exactly how we do it. We assume that this is true. Can you prove Pn plus 1? Can you prove Pn plus 1? Let's just write what Pn plus 1 is. Once again, replace each n with n plus 1. So n plus 1 larger than n plus 1 plus 1. So one statement in the first box, second statement in the second box. Can you prove that the first implies second? What? Well, similarly to what we just did, you can extract the first from the second. The second is longer, and so you can see n over here and n plus 1 over there. So what has happened, really? Not much. So you see the proof? No? You have an inequality, and you need to prove another inequality. The first inequality is visible in the second inequality. What are the rules of inequality? All I do here is just apply a certain rule of inequalities. What is that? I added 1 to both sides of the first inequality. So add 1. So, if x larger than y, then x plus 1 is larger than y plus 1, right? So that's the rule of inequalities. Okay? So indeed it works out in the sense that the first inequality, if it is correct, then the second inequality is also correct. Which means that the inductive step has been proven. But what? Well, there is no base. Okay, so right. So for some n, for 1, you need only one example to starting point, but it's never going to happen. So it's then this part proving that Pn implies Pn plus 1 is irrelevant. Doesn't give us anything because the initial statement is untrue. But what happens is exactly the same as what I just did here. This part was exactly the same as before. So assume Pn, prove Pn plus 1. You do not know technically, until it has been proven, you don't know that Pn is correct. So you don't rely on that. You just assume that it is correct and then derive Pn plus 1. Okay? Okay, so I have maybe a couple of more examples. Oh, here's one. N cubed plus 2n is divisible by 3. N larger than or equal to 1. Okay? So when you're given a theorem, you already know that it's correct, so you don't have to worry about that, and you just follow the procedure. Base, assumption, is inductive assumption, inductive step. So base, you can write out if you like, so base P, well, let me write what Pn is. Sometimes it helps to write these. So Pn is that statement, n cubed plus 2n is divisible by 3. So that's my statement. Base is P1, okay, which is 1 cubed plus 2 times 1 is divisible by 3. Well, certainly this is equal to 3, so it is true. So assumption, Pn is true. And now step, inductive step, prove Pn plus 1. Okay, so you have one number divisible by 3, you need to demonstrate that the other number is divisible by 3. Any ideas how that could be done?
Substitute.
Well, let me write out that number first. So Pn plus 1, let's take Pn plus 1, which is n plus 1 cubed plus 2n plus 1 is divisible by 3. Substitute this is how I would suggest to follow, is just to, rather than speak in terms of divisibility, you can just use the formula, remember? So you can just say that an cubed plus 2n is equal to 3k. That's divisibility by 3. So you don't have to deal with words, but just rather with formulas. And then you substitute. So substitute. So then I have my number here, and I have, I should expand, right? I should expand this expression before substituting. So I'll have n cubed plus 3n squared plus 3n plus 1 plus 2n plus 1. Okay, now then I need to find n cubed plus 2n, which is this. Okay, so I'm left with, I replace it with what? 3k. 3k plus 3n squared plus 3n. Hold on, why is it not working out?
Plus 3, because you have 2n plus.
2n plus 2, thank you. Okay. Plus 3. Okay? Which is divisible by 3. So the inductive assumption was used explicitly in the middle of our computation. Okay. I'll see you tomorrow.